Yeah. So last time, I think I need to. Yes. We saw, the syntax part of this first order predicate calculus with theories. Okay, the the syntax of first order predicate calculus. As just to jog your memory, first order predicate calculus, the way it's different from propositional logic is that it has set of non-logical symbols, which are the syntactic entities belonging to the theory or the type. These represent, predicate symbols, constant symbols, and function symbols, which represent operations, various operations on the domain. Okay, that are part of the theory, and yeah, and we saw one example of a theory is, of a theory, the syntax of it, for the non-logical symbols, for which is a theory intended to denote whose domain is supposed to be, the elements of the domain are sets. Okay, and there's an equality, it's a binary equality defined as a predicate symbol. And another predicate symbol denoted by epsilon is meant to be a binary relation relating to elements from that domain, which is supposed to intended somewhat as like inclusion or something. And of course, that what exactly it means will be determined by the semantics you give to these symbols. Then constant symbols denoted by symbol zero, which is supposed to denote a specific element in the domain, presumably the empty set. Okay, and in this particular case, it does not have any function symbols. This is the way that you introduce the syntax part of the theory, which are called the non-logical symbols. And we also saw an example of the non-logical symbols representing a part of a theory intended to represent which has these symbols. In addition to equality, a predicate symbol less than, a constant, multiplication. So we find all the syntax. I'm going to skip through those slides now. I'll get to the semantics. So in propositional logic, the truth of a formula was determined by a truth assignment for the prepositional variables, the prepositional symbols, okay, and that was the only thing that was that was there. So in a first order logic, since it has more than the logical symbols, specifically the non-logical symbols, you will have to just the truth assignment itself was considered as a model, was enough to define the model. Whereas here, model has to have more things in it. Specifically, it has to assign meaning to all the non-logical symbols that make up the in the formula. Therefore, the model has to have more information. Okay? So, the variable assignment will take values from the domain, as specified in the domain, as we'll see, will be part of the model. First, in a bit of the syntactic aspect of the that define the non-logical symbols, that is usually called a signature. Okay, the signature is a set of, that is just makes the signature contains all the non-logical symbols, the predicates, constants, and functions defined that make up the syntactic part of the theory. And given a signature sigma, then what is a model? A model assigns is used to assign interpretation or meaning to the non-logical symbols that form the part of that are part of the signature. Okay, so what it model consists of it assigns a non-empty set called a domain, which is part of the model N. We write a domain of N, and which is some set of elements. So the elements of that domain in the model are also referred to as the elements of the model. Okay, the way that we develop this thing, we assume for simplicity the case where we only have one domain. Okay, but this can be extended in a fairly intuitive way to logics that have multiple domains. Okay, multiple sorts or multiple types. So in which case you will have to have the model will also have to have one domain for each of them. But in this exposition, in this lecture, we will assume that we only have one domain, one domain single theory. Okay. Then what else? Then the model will have a mapping that assigns for each constant C, constant symbol in the signature sigma, an element denoted we denote it as C, the constant C in the model M of F. So it actually assigns a specific element belonging to the domain. Then we have another a map that is a function. For each function symbol F in the signature sigma, it assigns an actual function, okay? Function as a semantic object. And for each n-ary function, it assigns an n-ary function, which maps n, vector of n elements to some element, a single element in an element in the domain. And for every predicate symbol P in sigma, it maps a set of tuples of length n, for which that predicate is meant to be true. Okay, so you can. Yes. Okay. So that's what it does. So this is pretty much the model gives meaning, and sometimes that is usually called as interpretation. So these are the components of that make up model. Okay. Now, for example, for the set theory signature, set theory set theory example that you saw, whose signature contained a single predicate symbol epsilon and a constant symbol 0. One possible model for this could be where the domain could be the set of natural numbers, and epsilon we could map it to the less than operator on the natural numbers, and the constant 0 in the signature we can map to a 0. Okay? And then once you define your domain, then with respect to the domain, now you could define. We will formally define how you assign truth value given a model in the next few slides. But this is just I'm illustrating an example. Once you have a model and a variable assignment, you can then define things. Okay, so here I want to want to Yeah, so now you consider this particular sentence, which says there exists an X such that for all Y, it is not the case that Y is related by epsilon to X. What does this mean? Sentence mean in this model? So in this sentence, once you have the model, which gives interpretation to the various symbols in the signature, you could kind of interpret, give a truth value. What it says is that there is a natural number X such that no other natural number is smaller. Not remember that epsilon is less than, and so not less than means it is X must be greater than or equal to 0. It says in the model there must be an element X such that it is greater than or equal to every other element in the model. In this case, of course, this is true because there is 0 itself has this property, because 0 is an element that it is such that yes, it is not. It is there exists an X. Okay, 0 is 1, which that every element is greater than or equal to X. Okay, and you can see. So see here I've deliberately chosen, although set theory is meant to assign the domain is said to be of sets. Here I'm assigning a natural number. So you are free when you construct a model. You're free to assign whatever meaning that you want for these symbols. Okay, as long as they are appropriate functions and predicates. Okay, and here, if you want to interpret the elements as sets, each number here, the element represents the set, as it represents all the natural numbers, including up to and including that number. Okay. So if you want to interpret that set, because although that is, if you want to interpret a set, that's what it is. And pretty much this is, we are using the natural number in the domain to assign meaning to all the function symbol in the signature. Okay. Any questions here? Is this so? Yes, I'm trying to make the distinction between you have a syntactic part which defines all the non-logical symbols, and the model assigns meaning to each of those non-logical symbols. Okay. So to contrast, so in the case of propositional logic, the truth assignment S itself was the model. Okay, there was no, since it did not have any logical symbols, given a truth assignment to all the proposition variables, you were able to define the assign truth value for each of the formulas. Whereas here, you need to consider not only the assignment to the variables, but also the model which defines the interpretation for each of the symbols in the signature. Okay, so for example, here the model consists of 3 parts. One is the domain, okay, which in this case is natural number, and the meaning assigned to each of the logical symbols. Epsilon is mapped to less than in that less than operator over the natural numbers and 0. And so that's how you write it. And therefore now so here what we have is so just I just want to contrast. Okay, so this thing with Yeah. So the notation that I'm using is a little bit different than here. So I used these double brackets here. Given a variable assignment, you were able to define the meaning. And here, the syntax is slightly different. So here, given a formula phi, a well-formed formula, a syntactically valid formula in the logic, in order to define a truth, assign a truth to determine whether it's true or false, it has to be, you need a variable assignment given a model and assignment to the variables. Okay, so there are two components here, unlike in propositional logic, because it did not have any non-logical symbols. The models give meaning to the logical symbols, and so a truth assignment is determined by the model, given a model and a variable assignment. Okay, and that's how this will be defined. Okay, so whereas in the case of propositional logic, you only needed the variable assignment here. The semantic function will have a model and a variable assignment which assigns to each variable in the formula a value to variable assignment, which maps variables to elements in the domain. So the first part, so the rules that I'm going to show in the next few slides, tell you exactly how to assign truth value to every formula in the first order predicate logic that we have that we just defined. So this starts with first we'll have to assign meaning to formula built and various other formulas. So first you have to assign meaning to the terms. Okay, so that is defined first. So given a particular variable assignment S, which gives which assigns values to the variables. So that is extended, to S bar, which sorry, I had some problem with the. Are you all there? With my internet. Are you guys there?
Yes.
Oh, okay. So let me share my screen again. Yeah. And so it extends, if a term is just a variable, then its value is just whatever S maps that variable to, okay? So that's what it says. It extends uses S to extend it to S bar to assign a value to every term in the language. So if the term is just a variable, then S bar of X is whatever value that S maps that variable to. And for each constant symbol, C in the language, if the term is just the constant symbol, then S bar just assigns whatever the model maps that constant symbol to, which is that element C M in that in the domain. And if for any term which is constructed by applying the function symbol F to an array function symbol to n terms, T1 through Tn, it recursively first gets the value for each of those terms by applying S bar to each of the arguments recursively, and then applies the function that the model assigns F2, which is denoted as Fm, to those values. Okay, so that's how it's defined. So once you define, so this is like an evaluation function for the term. That's the only additional thing that you need. That is one additional thing that you need in here, because you did not have terms in prepositional logic. Okay. So once this meaning for the terms are assigned, now you could define the crux of the thing. You can assign truth value now to various formulas. Okay, so you start with atomic formulas, and then you assign. Then you move on to the more complex formulas, which are built using various connectives, logical connectives in the logic. Okay, so this so as you said, the one one of the atomic formulas is the equality one that is constructed using the predicate symbol equality. So that equality applied to two terms, T1 and T2, is true if and only if the value S bar, the value that T1 is assigned by S bar, is equal to the value S bar assigns T2. That is, the two values, the two terms should evaluate to the same value. So for an NRE predicate symbol, remember that the model maps each predicate NRE predicate symbol to a set of tuples. Okay, set of tuples, a tuple of values from the domain. So we say that the atomic formula that is constructed by applying P to a set of terms is true in the model N, given a variable assignment S, if the tuple of values that you get by applying S bar to each of these terms. That each of the terms that they evaluate to that tuple must belong. That atomic formula must be true, which means that must belong to the set that is assigned to P by the model. Okay, that's all. So that's how it is assigned. Because remember that our convention was that a predicate symbol is mapped to a set of values for which the predicate is intended to be true, and that's how it's done. This is another way of saying you have to evaluate that predicate. If the value that these terms evaluate to, that tuple is true for the predicate, then you assign true for that atomic formula. After that, then you define the semantics of more complex formulas recursively, just the way that you did in the case of preposition logic. So if it is the formula is constructed as a negation of a subformula phi, then that is true, given a model M and a variable assignment S only if and only if if phi is false, it's not true in the model for that variable assignment. Similarly, implication is defined in the standard way that if phi is false, the phi value is assigned false, or if it is true, then you have to have psi to be true in the model for that variable assignment. Okay. The interesting part here is the universal quantifier. So that is defined in the the way that you would expect. So a formula, a universally quantified formula constructed in this way, which quantifies the variable x, presumably appearing in the subformula phi, is true in a model given an assignment S. Okay, if and only if the intuition is that that should be true if phi itself is true for every, it is true when you replace, when you replace that particular x, the x inside phi for every element in the domain. If you replace, when you assign x to, so x, it must be true when you replace that x with for every element in the domain. So that is this is the notation. So S x bar d denotes the same as except it is the same. It's the same as S, except that x itself is mapped to a particular d, because the reason that it is defined this way is because phi, the formula phi, can have other variables besides x. So for that particular x, which this universal quantifier symbol quantifies, for that you replace that with d, leaving other things, and then you evaluate, and that this should hold true. This should evaluate true for every element in the domain. Okay. And this is just a very verbose way of saying that this formula, a universally quantified formula, should be true when I replace x with a particular element in the domain in phi, and then recursively apply the semantic function to phi for every element in the domain. So the question is, so this is something, there is a corner case here, which is usually not explicitly presented. So what happens when the domain, the model, for a model in which the domain is empty? Okay, because that's also a model. So if a model can choose to have the domain empty, okay? So in that case, what would the meaning of this thing be? Okay, usually the convention is to make a universal quantified formula to be vacuously true, true when the model maps the domain to an empty set. Okay. So so when it is empty, we consider, if the domain is empty, then you don't have any elements in it, in which case we assume that this is vacuously true. Since an existential quantification semantics, as I mentioned earlier, is defined as a derived operator, as the negation applied to universal quantified. So for a model whose domain is empty, the truth value of an existential quantifier will always be false. That's a side note. Okay? I'm just making. Any questions here? Okay. I hope it's clear as to how this kind of recursively applies the thing. So evaluating as truth value of a formula is done, kind of bottom up, starting from the atomic molecules. Of course, so here, unlike in the propositional case, because the domain there, I mean, had only two values. The variables were ranging over two values. So if you did have, here, since the, if you had a finite domain, you could do this kind of an evaluation, okay, over every element by enumerating every element of the domain. But if the domain is infinite, obviously you cannot use this method to, as a way to, you can't enumerate it, but semantically you could still kind of how how meaning is assigned. I mean, obviously you can't enumerate. I mean, where if it's an infinite domain, but even when there are, even for infinite domains, in some cases there are algorithms to, without enumerating the entire elements in the domain, you may be able to do so. But in general, doing it, whereas in propositional case, you could have some truth table or various, truth table assignment to literally is back. Yeah, my internet is very flaky today. Sorry about that. I don't know. These just, you guys back?
Yeah, I can hear you.
Hello? Sorry about that.
I can, yeah, I
I
think you're
think this
audible,
is the
sir.
way it will be.
Go ahead.
Hello. Yeah, let's maybe wait some time. Hopefully, sir will be back. Meanwhile, do you have any questions regarding the assignment? Is that how is that going? So the deadline for the rest of the problems will probably be sometime uh, early next weekish. Is that okay with everyone? How is I'm assuming everyone has been able to do the first two problems by Monday.
Sorry, what is the deadline for the distributions?
The first two questions deadline was last Monday.
Yeah, that is it. For the rest of
Yeah, so for the rest of them, it will probably be sometime early next week. Um, yeah, so if you have done the first two questions, the rest of them is not too much more code, but it's you have to run the like a lot of training. Like you have to retrain the network for various different configurations a couple of times. So that might take some time if training takes time on your mission.
yeah, I've seen that.
Mhm. But other than that, I think it's okay. Like I was just asking if you think that the assignment is easy enough or is it hard? Are there any issues while doing the assignment? I guess I'll take that as a no. In case if you guys have any issues, you can always just come to me. You can come to her. She can come to her. Right? Yeah, hi. Is everyone able to hear me?
Yeah.
Yeah, so just called sir. So it seems that his internet is not coming back. So sadly, we'll probably have to end the class right here because, like, sorry about the discontinuities and all. There will be some half an hour extra class at some point to cover the material of this class. As in, the sir will continue from where we left off here whenever the next class is, but we'll be, half an hour uh, late in some sense. So maybe there will be some extra class to cover that material at some point. So yeah, other than that, I think for now this is it. Unless you guys have some questions or want to talk about something, you're free to leave. Um, uh, Hi, Dhruvajyoti and Naveen. Do you guys want to talk about something?
Yeah, I'm just
Sorry, I couldn't make it out, but you can put it on the chat. So Dhruvajyoti, I don't think I can hear you. If you want to, like, you can also type into the chat. I'm looking at the chat.